All right, guys, I'm going to talk about a concept for enzyme purposes, for enzymatic reactions. It's called free energy. Okay. Now, what is free energy? You actually see it play out all the time in real life. For example, you might have a container, right, with, say, perfume. Over a period of time, as time goes by, the perfume particles that are in the container are going to diffuse out, right? They're going to diffuse out. Because the particles have free energy. They want to go to a state of disorderliness, right? Or entropy. Now, how do you actually explain it? There is another example for this, never worry. So the free energy that we have talked about is a concept in thermodynamics. It's also depicted as delta G. So another quick example which you might have encountered in, say, physics class, right? For example, what I'm trying to show here is a trolley on the top of a hill. And you can see my diagram skills are questionable here, but this is a trolley. It has potential energy. And because it's at this height, it has a lot of delta G. It has free energy, energy that is not being used yet. So it is not in a stable state. More free energy meaning not stable. So such a system is going to spontaneously change, and when the trolley gets to the bottom of the hill, it's more stable here. Because it's delta G, or the free energy has gone down. There is really no potential energy, and it has lost the kinetic energy in the process. So that's another way of looking at delta G. So if the delta G, or this free energy, if it decreases in a process or in a reaction, it becomes a spontaneous reaction. We don't need to do much for that, okay? Many reactions that we encounter in the body is not spontaneous though. Okay, they might need energy sources, they might need to get to a threshold level of energy, etc. Let's look at how does it apply to biological systems, or even to, say, chemical systems. You might recall that each of the covalent bonds that you have learned about, they have an energy signature. So say, for example, iodine and chlorine have 208 kilojoules of energy. Iodine and bromine, 175 kilojoules. And you can go on and on in this list. Even for organic molecules, oxygen and hydrogen, it is 413 kilojoules per second. Oxygen and carbon, 347 kilojoules per mole, right? So those represent energy existing in a chemical bond. So for example, here you have atom A that is bonded to atom B, and there is a certain amount of energy existing in this system. And along comes the particle C. So in the process of this chemical reaction, there will be an intermediate step where A, B, and C would be kind of equally aligned with each other. And they will be in a position of where they are exploring different options for the lowering of delta G, free energy. And it turns out A and C will create a bond because it creates lower delta G, free energy, while B is left out. Why am I telling you this? Because enzymes that we are studying, Enzymes are very unique. They almost take part in all these chemical reactions. They will make these things happen, but they never impact the free energy. So they are not going to change the chemical properties of the element. They're not going to change the bond energy. So the enzymes, clearly you have to remember, they do not change the free energy of the reactions. They can increase the rate of reaction. That's all they do. They increase the rate of reaction.